So far we have seen a PN junction, its capacitance, reverse bias capacitance, as well as its currents in all the regions. Today we will start discussing bipolar transistors. So okay, let's take a look at transistor, what a transistor is, and then we will proceed with the bipolar transistor. So far in the previous lectures, we've seen what a PN junction is, PN diode is. This is a symbol where we apply a voltage across its two terminals and I get a current through the two terminals. Right? The voltage across the two terminals controls the current through it. It's almost like a resistor, except that it is non-linear. You see that it in the forward bias, resistor value is low. In the reverse bias, resistor value is very large. This is an example of a classical two-terminal device. Only two terminals, P and N. You apply voltage across it, you get a current through the device from terminal 1 to terminal 2. Now let's take a slightly different kind of device. Conceptually, let's say it has two ports, P1 and there's a P2 port. Right? And the voltage of P1 controls the current through P2. Okay? This is something similar to your remote switch or a normal switch itself, where you do action on one port, something happens on the other port. Right? In this case, you apply a voltage on port 1, you get a voltage on the other, a current on the other port. Okay? Switch, if you switch on at one position, one place, the fan or a light burns in another place, right? It's similar to this. Okay? Though there is an electrical connection which is not visible to the naked eye, here it might be something else. Right? It could be electric field, it could be magnetic, could be anything. But let's say the voltage on one port affects the current on another, or could be anything. So it's quantity for port 1 affecting some other quantity on port 2. Okay. This is a classical example of a two-port, four-terminal. In the case of current, actually the current might just go through this port directly from here to here, right? Like an optocoupler. Right? You apply a voltage on one, it changes the amount of coupling on it changes the amount of light on the other port. So this is a two-port, four-terminal device. You could make it a two-port, three-terminal device by just making the third terminal common. And nothing magical about it, just a common terminal. The voltage across these two terminals affect the current through this terminal like this. So the ports are P1 and P2. One terminal is being common. This is a two-port, three-terminal device. Okay. In the special case where the voltage across one terminal affects the resistance across the other terminal. Okay. So the voltage, the control voltage here affects the resistance across these two. Okay. Where resistance means the relationship between VO to I, the voltage across the port to the current from the port. It is a trans resistor. Trans because this control voltage is affecting the value of this resistance, and it is a resistor between these two ports. So it's a trans resistor, right? And that's sometimes called as transistor. So let's assume you have a PN junction, right, to which you strap on another PN junction. Okay. So there's a PN junction here and there's a PN junction here. Okay. Remember, the diode was just this PN junction and you had contacted it externally through this. Okay. So to the base to the N type material, you add another PN junction here. Okay. And let's say you make the base width small. This region, N type region, small. Okay. We compress it for some particular reason, but let's assume that you have done that. So given that there are two PN junctions, for the drift, for no current to flow, you have an electric field here this way and an electric field here this way, and this is we have seen before in a diode, PN diode. And since these are two PN diode junctions, we'll have a inbuilt electric field here and an inbuilt electric field here. Depending on the concentration, we saw that the fields will change. Let's assume that this P type is more heavily doped than this P type. Then the field here is going to be larger compared to here. This is just marked out here. Now let's assume that this PN junction is forward biased. Right? then reduce the effective electric field as we've seen before in this depletion region, across this depletion region. And let this PN junction be reverse biased. So this PN junction is forward biased, this PN junction is reverse biased. Then the electric field here across this junction increases. So a whole current which was previously going from P to N will now, instead of being collected here because this waves width is very narrow, has a tendency to go across to this, across this NP junction and go around in this manner. The reason why this happens is, first of all, this is narrow and this field has become larger. So the hole that comes here gets swept across this junction before it can actually be collected out here. So the whole current, the minority carrier here, which was being supplied, injected from the p-type, actually instead of going out through this terminal, goes on across this reverse biased NP junction, PN junction, and then goes around like this. This actually constitutes a current in this direction. Some of these holes will actually combine with the majority carrier here, which is the electron, and you'll have a carrier recombination happening out there. The electron which has vanished here has to be supplied from the external world, or is generated in this body itself. So there's a recombination also that's happening here. Some of these holes which are going like this will recombine with the electron out here. Third, we have this PN junction, and we're going to have the minority carrier in the p-type diffusing, and we saw that in the diode, and that is an electron current which is going this way. Okay, you can see that here, because minority carrier in the p-type is the electron which then diffuses here, and that has to be supplied from the majority side. So injected from this side to this p-type, diffusing here and then going across like this. So the electron current, we know, goes opposite to the flow of electrons. So that also goes this way in the direction of the whole current. Take 2 minutes to see this video to understand what's happening out there. Okay. This material on which the two junctions are formed is called the base. This is the base material on which you form the junctions. This p-type is emitting the holes. Okay, you saw that, right? This is emitting the holes, it then diffuses here. This injects the hole or emits the hole, and it's called the emitter. This p-type actually is collecting the holes. You can see that, right? It's collecting the holes out here. Hence, it's called the collector. So you have the emitter, the base, and the collector. Emitter current, as you can see, is going into the terminal here, right? Because the hole is going this way and the electron is flowing this way. So electron current is also going this way, hole current is also going this way. Is the hole current plus the electron current. Okay. Since the current is constituted both by the hole and the electron, it's called a bipolar. Okay. Actually, a PN diode also is bipolar from the diagram, right? So we have got both the hole and the electron current. Base current IB is flowing out of it because the electron is going this way. The base current is coming out of this terminal. Is the electron current plus the recombination current. You remember, for hole coming from here recombines with the electron, and that electron has to be supplied also from the external world. So that is recombination current plus the electron current. And the collector current, you can see the hole which is going through this, okay, plus the minus the hole that actually recombined here, because not all the holes reach this point. Right? Some of them recombine with the majority carrier, which was the electron. So it is the hole current minus the recombination current. Right? Because not all the holes that are injected from the emitter tend to reach the collector. Some of them just recombine here. This hole current is actually controlled by the VBE, because this junction is what's defining how much current is flowing. If this is a reverse bias, it just helps pull the hole out from here rather than getting it to IB. So it is not that sensitive to the VCE as much, but it is set by the VBE. Hence it's called a transistor. It is the current in the collector is controlled by a voltage across the VBE or VEB in this case. So IE, the total current you can see from here is IB plus IC. The two terminals which the IE is the current going into the emitter here, IB is the current coming out of the base, and IC is the current coming out of the collector. So IE equal to IB plus IC. And you can check it here also. IE will be equal to this plus this because the recombination current will cancel. You get the electron current plus hole current, which is this. It's a fairly simple, simplified structure of the current, but fairly good enough. This is actually called the PNP bipolar transistor. Where does the PNP come from? PNP. This is what PNP stands for here. Bipolar because it's a bipolar transistor. The current is because of the hole and the electron both. And transistor because the junction voltage across a different PN junction controls the collector current. An electrical symbol of PNP bipolar transistor is an emitter. Emitter base is exactly like the diode symbol that we talked about, emitter to base, and base to collector is this. We don't draw a symbol out here because it's assumed that this is going to be, if once we know this polarity, you know what this is. So this one, P side is here, this is N, so this is also P. So you always draw the arrow only in the base emitter junction. So emitter, base and collector. Now, we saw that the base current is a combination of electron current and recombination current. Electron current depends on the base doping. And the recombination current predominantly depends on the base width. It depends on base doping as well, but base width as well. So this factor that combines this is the base width mostly. IE is approximately equal to IC, but it's not exactly equal because of the recombination current that we have in between. So the efficiency of the transistor in a way is called alpha, which is the current efficiency, is the ratio of IC to IE, the amount of current that the current reaches the collector to the amount of current injected from the emitter. And this is typically 0.9 to 0.99, 90% to 99% efficient. Right? The remaining 1% or 10% goes into the base. This is called the current efficiency. Beta is another ratio that we talk about typically, is IC to IB. The ratio of the collector current to the base current. And this typically is very large. In a good transistor, this can be as much as 400, 500. But in typical IC applications, it might be 50, 60, maybe even 100 sometimes. But there are some bipolar transistors you'll see later who will have a beta of less than 1 or about 1. But we'll talk about that later. So this is the current gain. Okay? Because this is the ratio of the, it's almost as if though if IB flows in, IC comes out. Or IB flows out, IC also comes out. So this looks like a current gain. So just take these two definitions and the fact that IE equal to IC plus IP, you'll get these relations very easily. Just try proving it to yourself. Alpha is equal to beta plus beta plus 1. Now, we see the bipolar transistor, we just NPN we saw, PNP we saw. Just instead of PNP, we'll talk about an NPN transistor now. The base being the p-type material, and then you make the emitter as n-type and the collector as n-type, and you forward bias the base emitter junction, which is this. So you forward biasing the base emitter junction. Okay. So the E1 without the bias is in this direction with the large one, and E2 is in this direction. Okay. Because we are forward biased, the E1 will actually reduce, and then you reverse bias the collector emitter collector base junction further, so the field across this increases. Here instead of a hole current, an electron current will flow from the emitter through the base, and instead of being collected at the base, will get swept across the base collector junction. Remember, this width is so narrow that it hardly finds time to get through this. The field which is present here just sweeps it across. Right? So instead of the hole current, you see that's an electron current. Same way, some of these holes, some of these electrons will recombine with the hole in the hole which is the majority carrier in the p-type material. That also happens. And the minority carrier diffusion in the n-type, which is the hole, that current will also exist. It will get injected from the base into the emitter, and here it diffuses and this current keeps flowing. So it's almost exactly like the PNP, except that the minority carriers doping profiles have changed, so the minority carriers have changed in the base emitter and collector. So this is the n-type material which actually emits the electrons into the base where it becomes a minority carrier and just goes through and gets swept across the base collector junction. Since it emits electron, it's called the emitter, and since this collects the electron, it's called the collector. Right? So we still have the same emitter base collector concept, except that the dopings are N, P, and N instead of P and P. Okay. Emitter current again. Here, if you notice, the hole actually goes through this and the electron is going in. So if the electron is going in, the electron current is going out of the terminal. Hole current is also out of the terminal. So it is a hole current plus the electron current, but going out of the terminal. In a PNP, it was going in an NPN, it is coming out. The same reason why it's called bipolar, because the current is because of both the electron and the hole. Base current flows into the base because hole is going in here. Right? This is basically the hole current plus the recombination current. This hole is both the hole current that is flowing in as well as the some of the electrons recombining the hole, and that hole also has to be supplied. So that is the recombination current. And collector current is electron current minus the recombination current. Not all the electrons that are flowing from here reaches the collector because some of them recombine with the hole out here. Okay. Same reason, it's controlled by the VBE, hence called a transistor. IE equal to IB plus VIC, because IE is the one that's coming out, IB goes in, IC goes in. So sum of these two current has to be same as IE. There's no other third terminal, fourth terminal here. This is your NPN bipolar transistor. Okay. A symbol for the NPN bipolar transistor is given here. Again, the arrow is marked only in the base emitter junction, and since the base is P-type, emitter is N-type, the arrow is in this direction. Okay. And the collector is out here. So current in the emitter actually comes out. The other way of looking at this, the arrow is the current actually flows out of the emitter, and hence it flows out of the emitter, it flows in to the rest of the two terminals. Base current flows this way, collector current flows this way, sum of those two flows out of the emitter. Bipolar transistor. What happens when the base width is much larger? We've seen what the bipolar transistor is. We've seen that it has got a emitter, base, and a collector. What happens when the base width is made larger? The minority carriers have to travel more in the region. It's the majority carriers were emitted by the emitter, and they enter the base where they become minority, and they have to travel more distance because the base width is larger. If it has to travel more distance, the chances of recombination increases, which increases the base current, as well as reduces the collector current by the same amount, because the recombination current is added to the base and removed from the collector. We've seen that. This actually reduces to a drop in the beta of the device, because beta is nothing but collector current by base current. Collector current is reduced, base current is increased, so beta drops. In a typical CMOS process, uninterrupted bipolars have base widths of a few micron. Beta of these devices are sometimes in single digits, sometimes 2 or lower. This is what I was talking about earlier. So some very good bipolars might have in the 50s or even 100s, but uninterrupted bipolars in CMOS processes can have single digit betas. Let's talk about bipolar IV characteristics. So bipolar device, we'll talk about NPN, and PNP is similar. NPN device with a collector, base, and terminal junction. The electrical symbol is this, right? Where the terminal voltages we'll just talk about. V2 emitter, collector to emitter is called VCE. Collector to base is VCB. Base to emitter is VBE. Typically, we'll keep talking about these. VCE and VBE, because VCB is nothing but the difference between these two voltages. Okay. So we'll draw VCE versus IC, right? The amount of voltage across this and the current through these two terminals controlled by the VB for various values of VB. Because we know that the current through VCE, current through the collector is a function of the VB. Right? So we'll just draw collector current is a function of VCE for various values of VB. So for very slow values of VB, we know that this forward bias junction is not even turned on. This PN junction is not even turned on. It's below its cut-in voltage. So no current flows. If there's no current through the emitter, there's no current through the collector. And this region is called the cutoff region, where there's no current flowing through the device. Okay. Now as you increase VB, okay, some amount of current will start flowing, okay, now through the emitter. But how much of it will get collected by the collector or what influence it has, we'll just see. Right? So for small values of VC, now the current is actually not large. Even though this is setting the current to, this junction is saying, okay, set the current to some value. Because VCE is 0, it's not able to collect the current, hence the collector current is very low. And as the collector current, as the collector voltage increases, it is able to collect all the current, hence the current increases. But you see that it doesn't increase a whole lot because this current is actually set by the value of VBE, not by VCE. The VCE has a small impact on it, but not a large impact. So current tends to saturate after some time. Okay. Now if you increase VBE, the current obviously increases. Initially the same thing happens. Initially the VCE is not large enough for it to collect the current, but once it starts collecting all the current, it kind of tends to saturate. But you can see a very small slope here. As you increase VCE, there's a small change in current. What really happens is as you increase VCE, the reverse bias in this junction increases, the depletion width in this region increases. If the depletion width region increases, the recombination current actually reduces. And it's also able to collect more of the electrons that is emitted by the emitter into the base. So the collector current slightly increases, right, with the increasing VC. This actually sometimes is referred to as the early effect, but it just gives you a small slope. If you increase VBE further, the current correspondingly increases, right? And this goes on. Right? For various values of VBE, you can get various values of currents. Okay? This region is called the forward active region. It's forward because the base collector emitter junction is forward. Now, when the VCE is actually very small, okay, this current is cut off, not cut off. So there is very little current through the from the collector because the VC voltage is small. But it could be that both these junctions are forward biased. Right? Because when VC is small, VCB can be positive. Remember we talked, it's because of the difference between VB and VCE. Right? So even this can be forward biased at very small values of VCE. Right? And when that happens, there is a lot amount of charge in both these regions. And typically we don't want to be operating in this region at all. Right? This is called the saturation region. Now we'll just draw a table of base collector junction versus base emitter junction biases, just to see the various regions of operation. Right? Since there are two sets of terminals, there are going to be four combinations. So based on the bias, we'll categorize the regions. Okay? So when the base emitter is forward biased and the base collector is reverse biased, that is this region, right? Base collector is reverse biased and base emitter is forward biased, we get the forward active region. When the base emitter is reverse biased and the base collector is also reverse biased, we get the cutoff region. No current flows. When the base emitter is reverse biased and the base collector is forward biased, this is an interesting case, right? What do you mean by that? When base emitter is reverse biased and this is forward biased. See, this is almost like a symmetric device, except that the emitter is actually heavily doped compared to the collector. So when this happens, it looks like a transistor in the reverse direction. emitter is now acting as a function of collector, and collector is acting as a function of emitter, right? Except that the emitter is not more lightly doped, and collector is heavily doped. So it's kind of a bipolar transistor, but not a very good one, because emitter is lightly doped, right? The currents will be lower. The collector is not as good as the previous collector because it's heavily doped. The depletion regions hence will probably get through right through. All those issues will be there. It's not a symmetric device from that angle, but still it's a bipolar in the reverse direction. Right? So this is called the reverse active region. The currents will be fairly similar, but will not be the exact same magnitudes. It in fact will be much lower. Right? The betas will drop, the alphas will drop, everything will happen. Lastly, when both these junctions are forward biased, this is forward biased and this is forward biased, it happens to be in the saturation region. This is something we really don't want to operate on because both the base base collector and the base emitter are forward biased, right? And you really don't get too much of a transistor action, and there's a whole lot of charge sitting out here. We'll just take a look at NPN logic circuit. Let's just do two problems to quantify the learnings that we had so far. Let's say we have a bipolar transistor which has a base resistor and a collector resistor. And the base is connected to a voltage source VB. The collector resistor is connected to a VC, right? So this is kind of we have biased the base and biasing the collector. Emitter is a common. Remember, this is exactly like a three terminal two port network. This is port 1, this is port 1, this is port 2, but there are only three terminals, 1, 2 and 3. So this is a transistor is a classical example of two port, three terminal device. Okay. So assume that the beta of this transistor is 100, VB is 0.7, VCC is 3 and VC is 0.1 volt. When this happens, find VB when VB equal to 0. That means you are not even biasing the base. What is VC? Should be relatively easy. When base is not biased, there's no current, so you should be able to find this easily. Okay. When VB is now biased with a 3 volt, find RB and RL such that VC, the collector voltage is this 0.1, VC is set, and the collector current is set to 1 milliampere. So this is called biasing the transistor. You're going to choose RB and RL given these external voltages such that there is a set of terminal voltages set on the bipolar transistor as well as setting the current IC. This is called biasing the transistor. You choose RL and RB. Okay. Now you'll find some value of RB. What would you do to reduce RB? RB might come to a large value, right? Sometimes large value resistors take more area. You don't want to have them in silicon circuits. What will you do to reduce RB? Right? You'll have to concentrate what happens here. You can do something out here. You can take a hint from the next problem if you want to. But this is something that you would want to discuss and figure out what needs to be done to reduce RB. Okay. Second problem. So this first problem dealt with biasing the transistor. Now the second problem is kind of a little bit of a gain circuit. The same transistor, instead of a RB, we're now going to put an RE, a resistor in the emitter. We retain the RC. We call it RL, we call it RC here. And we call this port as Vin and this Vout. Right? The voltage here is called Vout, this voltage here is called Vin. Remember now the base emitter is not same as Vin. Base emitter voltage is Vin minus emitter current into RE. So that's a slight change in this circuit configuration. You must have done this in your circuits class. Assume the same kind of transistor, right? Given that RE is 100 ohms, RC is 1 kilo ohm, find Vout in terms of Vn. Okay? If what happens if Vn slightly increases, what happens to Vout? Okay? The ratio of Vout to Vn is called the gain of this transistor, gain of this configuration, not the transistor, sorry, gain of this configuration. You can see that if Vn actually increases slightly, you would expect that that's Vn is Vb, so V will also tend to increase quite a bit. So the current through the resistor actually will increase because the other end is ground. So the emitter current increases, which means the collector current will increase. If the collector current increases, this voltage will drop because this voltage is fixed. The voltage drop across this will increase, so this voltage Vout will drop. So an increase in Vn is reducing the Vout. Right? So you get Vout by Vn as a negative quantity. It's actually a negative gain. Check this out. Okay. So once you understand that, you'll be able to do your circuits a little bit more easily. At what value of Vn, right? At what value of Vn? Remember, Vn is not Vb. At what value of Vn? VCE is Vsat, right? VCE is not V out again. VCE plus IE into RE is V out, right? But what we want is VCE equal to Vsat. Just check that out. Because below that, the transistor will enter saturation region, and you really don't want to operate transistor in the saturation region as we seen before. So what value of Vn what is the maximum value of Vn such that the transistor doesn't enter saturation region?